Today I'll share about like basic stuff, Sumcheck, and if we have time, we can go a bit on like GKR stuff as well. Okay, so I guess like first of all, like motivation of why we need Sumcheck is basically okay. So like, okay, let's write it. So yeah, feel free to stop me along the way. So I guess the motivation is that prover P wants to prove like H is a sum of like a polynomial is sum of a polynomial multivariate. So let's say it's like multivariate of f, where we could have like f1, x1, x2, and multiple x, I guess. So an example would be like h, right? If it's like a 3 variables multivariate, it would be like a combination of f 0, 0, 0 plus f 0, 0, 1 plus f 0, 1, 0, and all the combinations, right, including like all the permutations and combination up until like 1, 1, 1, right? So this is for like 3 variables, so it's still manageable. But imagine like this multivariate could be like a very large multivariate. So for the motivation, I guess, is like we want to outsource the computation to a prover that can do this heavy computation, whereas the verifier should only do light verification and still manage to verify that this value is indeed equal to this. Yeah. So yeah, I guess. Yeah, the protocol will look something like this. The protocol of Sumcheck will look something like this, which is P will actually do the entire calculation of this. So first of all, P calculates the actual value of H. Okay, and then what P will do is P will calculate the partial sum of the partial sum. I'll name it like G here, G x, leaving like G1x, leaving x1 free. Okay, so I guess like what that means is that the partial sum of gx1 is that, okay, back to this example, right? We are taking like a polynomial multivariate of 3 variables. It will be like f x1 0 0 plus f x1 0 1. So all the combination except like x1. So x1 is an unknown variable. Okay, so like f x1 1 0 plus f x1 1 1. Is everything okay here? Yeah, and based on like the Schwartz-Zippel lemma that is explained by Harry last week, we will take a randomness from the verifier. So we'll get like a randomness R from the verifier, and we can like, so this is the partial sum is like a constant, right? Like that is computed by prover and sent to the verifier, and we'll get this randomness R, put it into like substitute x1, and we'll get like fr 0 0 plus f r 0 1 plus f r 1 0 plus f r 1 1. So the verifier will compute this, and the prover will also compute this, and the verifier just need to check that it's matched, and you can verify like basically what is provided by the prover on the partial sum is indeed a correct thing. So I guess like step 3 of the protocol is just like V, the verifier, checks the partial sum, which is through this.
The variables are not necessarily binary values, right? Or are they just 0 and 1?
Which variable?
Like x2, x3, x1, x2, x3.
X1. So I think this is like a Boolean,
Oh, okay.
a Boolean multivariate. So it's like a 0 or 1. Yeah.
I think
The variables are the elements on the parent field. Yeah, the parent field.
they're not necessarily Boolean.
Yeah.
Yeah. Okay. So it's not Boolean.
Because R is a random number.
Okay, so I missed a step here. Okay, so basically when the prover computes this partial sum, it first checks that this partial sum, like this for partial sum is indeed equals to h. Okay, check partial sum is equal to h, and then it will only then make sure that the partial sum is correct. So like v sends r to p. And P takes this R and compute this. So P takes R and compute this. Okay, and yeah, and I guess like this is only for the first variable x1, right? So what the prover will do is repeat the process for the second variable. So meaning like it would do like a gx2, and then taking this r and leave like the variable x2 to be free, and then yeah, do the same computation, and up until it completes like all of the so this is like consider one round, right? Like one round of leaving the first variable empty and computing a partial sums, and then repeating a process of like leaving the second variable empty and computing a partial sums up until it reaches the last variable. And if the prover can prove that all the partial sums are correct, then they are basically proving like the sum of h. Yeah, so I guess like the motivation of this is that instead of the verifier having to compute the entire evaluation of this, it now only need to compute like a log n evaluation, because rather than computing like, let's say like 2 of n of this, it now only needs to compute like n of this. So we improve like the verifier verification time to log n. Okay, I think that's like Sumcheck. Any questions? Okay.
Sorry, did you say you needed to have a lot of variables for the proof to be sound, or if you have too little, it's
No, I think you can have any number of variables, but the motivation for the Sumcheck protocol is like if you have a large number of variables, and the verifier doesn't have like the computation power or don't want to do it themselves, they can still outsource this computation to an untrusted prover. So the prover will do this computation for them, but it's still verifiable that they're actually doing the computation right. Yeah. I guess we can, if we want, we can do a little bit of GKR. Okay.
Where does Sumcheck fit into the map of the smart code? Like, where is it actually used?
I could try and fill that.
Yep. Thank you.
So Sumchecks are starting to get used everywhere because they're much more efficient ways of. So they fit into the polynomial interactive operator layer. So for example, we use them with Aztec. So we modified clock to use Sumchecks that originally came through with Hyperclock. The scheme Hypernym uses Sumchecks, whereas no previously nobody did. Because Sumchecks are very powerful because they're linear timing. You can evaluate expressions over these multilinear polynomials in linear time without having to perform any fast Fourier transforms to polynomial arithmetic, which the computing techniques require, which makes it very efficient at the cost of working with multilinear polynomials instead of univariate polynomials, which is slightly annoying because it requires multilinear polynomial coordinate schemes, which are more complex than univariate ones, but it's typically it's a very valuable trade-off to have.
Okay. Sorry. So yeah, I guess like like what's the use of Sumcheck, right? Maybe like GKR is an example. So, okay, sorry. Yeah. So I think I'll just go through like the most basic GKR protocol. Oh, sorry. Yeah, most basic one where all the, like, the inputs is public. So I guess like just a very high level intuition, GKR is used to do like verification on arithmetic circuit. So maybe we'll start like on a high level protocol of how it actually works. So first of all, the prover and the verifier will agree on a circuit that they want to prove, and the prover will tell the verifier what's the output of the circuit. Output of circuit. Yeah. So I guess like, yeah, maybe an easier example is like, say you have a circuit of like gates, right? Like, so let's go through an example. So these are just like the circuit, the gates in the circuits, right? And then you can have like multiple more, right? Like up until like, so this is like the output of the circuit, and up until like multiple layers, and you have like inputs of the circuit. So I guess like high level intuition is that we will see this circuit as one layer for each layer. So this would be like one layer. This will be the second layer, and so on and so forth. So let's say this is like layer 0, layer 1, and we'll perform a sum check on each layer of the circuit, starting from the output layer. So if we come back to this protocol, the prover tells the verifier what's the output of the circuit, so the evaluated output of this. But of course, like the verifier can't trust the prover, right? So the prover will do a sum check protocol on the last layer of this based on the claim input of the previous layer, and then recursively do it down up until like the first layer of the input. That's like the high level. So I guess like we can just like work through an example and see how it actually works. So yeah, let's I guess like name this output as like V00. So maybe we can do a convention of like, this is layer I. So we'll do like Vi and I don't know, like X or something. Like this is the number of gate. So at layer 0, we have like V00, V01. Oh. And then this is like layer 1, V10, V11, V12, and V13. Okay. Yeah, and if you look at like this example circuit, you can basically form some equations around this. So like V00 is basically like V10 multiplies by V11. V01 is V12 plus. So this is the addition gate, this is a multiplication gate, plus V13. Yeah, and I guess this two is also equivalent to like V00 equals like 0, V10 plus V11 plus 1. Yeah, so this part is like the addition gate, right? So we are just extending the equation. So this is like the addition gate, and this is like the multiplication gate. Okay. Thank you. Oh, okay, this is nice. Yeah, and we can actually do like make it to be like a generic equation of so vi z. Okay, maybe I'll do it as z. Okay, equals to the sum of so in here I define like x as like the left gate, y as like the right gate. Okay. So the left hand side is like the not the left hand side, but the first term is like the addition. So like the addition gate of the addition gate of the previous layer. So if this is like layer 0, then the addition gate of this vi plus 1 x plus vi 1 y plus, and then the multiplication gate vi plus 1 x and vi plus 1 y. Okay, does that make sense? No? Okay, which part of it doesn't make sense? Okay, like from here or to here, or? Okay, so I guess like if you want to think about it, this can also be formed. So we sum against like all the combination of like the layer of the previous. So we are doing like, okay, the only one that is connected to from this gate is like v10 and v11, right? But we are doing like a combination of all the gates. So we are also doing like v10 plus v12, for example, v10 plus v13. So this and this and this and this, right? But they're not connected, right? So if they're not connected, there will be like this 0 in front. So eventually it's not added. It's not added to the actual one. So that's the part of this here, which is we are summing up all the combinations of the previous inputs. If they are not connected by wire in the circuit, then it will be assigned like to a 0 to form this generic equation. Does that make sense?
Why there are two sum single?
You mean this sum?
Yeah, there are two. Why there are two?
One for left and the
Yeah.
other for the right.
Yeah, one for left and one for right.
Okay.
Yeah. So yeah, I mean like we are doing all the combination, right? So like we'll do like also v1 plus like v12, and including the multiplication. So we'll also do like v times v12 and so on and so forth. If they're not connected by wire in the circuit, then we just assign it 0. If they are, then we are assigning it as a 1. Okay. Yeah, exactly. So I think we want to make it to not just binary gates, and we do it through like a multilinear extension. which is, I guess, like what I'm going to talk about next. So currently this is all like Boolean gates, right? Like Boolean, and we want to do it to become a polynomial. So we'll do like a, okay, maybe I'll rub this off. Yeah, so I guess like maybe we first need to understand a little bit on like multilinear extension. So essentially like turning this Boolean multivariate into a polynomial. Yeah, so you have like this multivariate up until like x m. And what it will does is essentially just sum up all the combination. Okay. So I think this is a little bit confusing, but yeah, maybe we can like walk through an example to make it easier. So for example, okay, let's do like a two variable multivariate like x1, x2. If you want to do like MLE on it to make it to a polynomial function, you would take up all the you would look up at all the combination. One sec, I'll just so this is like all the combinations of that's possible in this like Boolean multivariate, like G00, G01, G10, and G11. And we see if it's like equal, if it's equal to like, if x and e is equal to, if x is equal to e, then this will evaluate to 1. If it's not, then this will evaluate to like 0. So depending on whether we want to take in the value of this, this evaluated constants. Yeah. So.
Sorry. So an EQ thing is something that you define.
Yeah, EQ is equal.
Oh.
Yeah.
Okay.
So, yeah, equal. I guess like if x and e, like the function of equal is just like if x is equal to e, then this evaluate to 1. If it's not equal to 1, if they're not equal, then it's evaluate to 0.
Okay. So it's a function that you assign. You define.
Yeah.
You define it.
Okay, yeah. Maybe I'll do this like equal.
You can see it at another range polynomial.
Okay, yeah. Like that.
Yeah. Something like this, right? 1 if x equals e, 0 otherwise. Okay.
So here, that fall equal, they are the same.
Which one?
So this example is so all the equal are the same or they are different. Are they same or different?
I think they're the same. I think.
What? What's the question?
That for EQ
Cool. Yeah.
Yeah, that's the same.
function are they same or they're different? Because
I think the
like-
parameters are different.
Okay, that makes sense.
So the EQ definition is the same. But in this different presentations, they just pass one parameter into one vector into EQ. That thing there's an implicit parameter inside. So in that case, the EQs are different from each other. But
Yeah. So it will actually be something like this, like this equal x. So I'll now expand this term, okay? So it'll be like G00 x1. So x1 is an unknown, right? x1 times e1. E1 is 0, right? So e1 is a known term, plus 1 minus x1, 1 minus e1, if that makes sense. So so here e1 is like 0 because we already know the value of 0, right? And then we also need to do like for x2. So it would be like x2 minus e2 is also 0, right? So this is 0 plus 1 minus x2. x2 is an unknown, we are not sure. And then 1 minus e2, which is e2 is also 0, yeah. And then this is the first term, right? This is the first term of this entire thing. And then we'll like plus g0, 1. So in this case, x1 times e1. e1 is still 0, plus 1 minus x1, 1 minus e1. So e1 is still 0. And this is x2 times. So e2 right now is like 1, right? So 1 plus 1 minus x2, 1 minus 1, because this is e2 and e2 is 1 this time. And then, yeah, you'll do the same for the remaining two terms, if that makes sense.
I think there's something missing. We have to ensure that the x and the e both on bits, not the element from the. So you imagine that x equals 1 and e, sorry, the L or e, the second parameter of EQ.
Which one?
For this,
Yeah.
This definition,
Yeah.
is e, right? L
Yeah.
or e?
E.
E, okay. So imagine that x equals to 1 and e equals 2. Okay, that definition, you know, you cannot say that, okay, equals to 0 otherwise. So there's a requirement that both x and e are bits.
Yeah.
Yeah.
At this point, I think it is still the Boolean.
Because I think the parameters here are quantified by a sigma outside sigma notation outside to ensure that they are both of them are bits instead of elements from the parameter field.
Okay.
Yeah, that's a small.
I see. Yeah. So I guess like this is how you extend it to be a polynomial from a Boolean multivariate. You would like do the equals, check whether the equal sign, and evaluate all possible combinations. Does that make sense? Okay. Yeah. Yeah, I guess the point is, why do we want to make it into a polynomial in GKR?
Sumcheck.
Yeah. Oh, yeah. Okay. Yeah. Okay. So I guess like back to this protocol, the prover will. So this output is like public to verifier, right? This output is public to verifier. So what the prover will do is the prover will check that the prover will do the evaluation that this output is equivalent to the sum check of this layer of the circuit. Oh shit. Yeah. So the prover will first like turn this Boolean gate into a polynomial through like this multilinear extension, and then prove that the output of this equation is equals to the constant. So like because this is like a constant, right? Essentially the output is already known to the verifier. Yeah. So in that sense, the prover essentially already proved like one layer, which is like the inputs to this layer of the circuit is correct after doing the sum check on this layer of the circuit is correct and equivalent to the output of the circuit, which is this public output. All right.
And it moves down along the.
Yeah, and then it moves down to the second layer. So for the second layer, we don't like the output of the second layer one. The output of the layer one is not public, right? It's not public to the verifier. So because this is the whole circuit, so that's why the output of layer 0 is public to everyone. But the output of this is not public. Only the prover knows what's the output of this. So the prover will just make a claim on the output of this layer one. So what is like the prover would just say is like, okay, the output of this layer one is like maybe like something x, okay, and then the prover will do the Sumcheck protocol on this layer. So again, the prover will make this Boolean gate into this multilinear, make it into a polynomial, and do the Sumcheck to check that the inputs to this polynomial equation is equivalent to the claim output of this. So this output is claimed by the prover. So the prover says what it is, but it's not trusted by the verifier, right? Because it's just a claim output. But the verifier can verify that the Sumcheck is equivalent to the claim output of it. But because the claim output of this is also the input to like this one, so yeah, the prover will just eventually move down up until the input layer, and yeah, again like back to the same method of like the Schwarz-Zippel lemma or something like that. Yeah, the verifier would need to send a randomness for each layer of the each layer of the Sumcheck. So if like there's 4 layers, let's say if the circuit is like 4 layers, the verifier would need to send 4 random variables. Yeah, because we are doing a Sumcheck protocol on each layer of that, up until like the input layers, up until like this last input layers, the inputs to the protocol is again public to the verifier. So the verifier can check that the inputs is indeed like the inputs of the circuits. Let's see what else. Yeah, I guess that's mostly it maybe. Yeah. Sorry for being a bit messy, but yeah.
Oh, I got a quick question.
Yeah.
Is there like some sort of optimization in the paper that allows you to combine everything into like a grand, a super Sumcheck protocol for all layers, and you can do it in one go?
Like what would that look like? Like
I don't know. I'm just gonna say. Is there a way? I mean, is there like an optimization perhaps in the paper for you to combine all layers to make one big equation, and then you do Sumcheck on that big equation instead of having to go layer?
Oh, okay, you can do that. Okay, layer by layer.
Yeah, you have to go layer by layer.
I think more layers you can get more performance, from different criteria. I think that the power of GKR just comes from the layers. I mean, if we have one layer, we will compute over a very huge Sumcheck. Well, if we compose that Sumcheck into different layers, in each layer we will get